In the last video, we looked at our first examples of how resonance can influence reactivity. We looked at how, specifically, how resonance can help stabilize either a conjugate base or a conjugate acid to influence acid-base chemistry. So what we're going to do in this video is we're going to look at another reaction, and this is just going to be an addition reaction, and we're going to be adding HX or HBr to a diene. Okay, so it's going to be a conjugated olefin. So that means we're going to have more than one double bond, two double bonds connected with each other. We're going to end up with a very interesting circumstance here where we'll have one set of conditions which control the speed of the reaction, and another set of conditions which control the thermodynamics of the reaction. So we'll be able to get different products or different product ratios under different reaction conditions. So before we do that, let's just look and remind ourselves about the stability of some cations, because that's what we're going to be looking at as intermediates. Alright, so here we have two sets of three carbocations. And what we want to be able to do is rank these carbocations in order of stability. Alright, so let's look at this top set. So what do we have here? We have a secondary carbocation. Does that double bond matter at all to that secondary carbocation? No, not really, because we have here, we have an sp3 hybridized carbon in between the carbocation and the alkene. All right, so there's no delocalization, no resonance. All right, what about the next one? Oh, this is just a standard secondary carbocation. And what about the third one? All right, the third one has the circumstance where we have a cation on a atom next to a pi bond, right? So in this case, we have the possibility of resonance like this to give us a new resonance contributor. We have the double bond here and a plus like this. All right, so here we have resonance. And what's that going to do to the stability of the cation? Right, that is going to make this cation more stable. Right, so this is a single cation that's able to spread the electrons between those positions. Okay, so this one here is going to be the most stable. Okay, the other two are going to be about the same because they just have localized cations. All right, let's look at the bottom three. All right, so what about that first one? Can we have resonance in the first case on the left side? Yes, we can have resonance like this. So remember, we use this double-sided arrow for resonance. We can get this cation, so notice, even though this first one didn't look that great, right, because this was only a primary carbocation, it has resonance between a primary and a tertiary position. Okay, so this is what we call an allylic carbocation. Okay, and it's between primary and tertiary. Let's look at the next one. All right, this one also has a cation next to a pi bond, so we can draw resonance. And we get this resonance contributor like this with a plus over here. This is also an allylic carbocation. What kind of positions is it spreading that plus charge between? Right, this is spreading it between a secondary and a primary. Okay, and then the last example, of course, there's no pi bonds at all, and so this is just your standard tertiary carbocation. All right? So in general, the more resonance we have, the more stable the carbocation is going to be. So we could likely say that the carbocation that's spread between tertiary and primary is going to be more stable than between secondary and primary. And this one has tertiary component here, so and it's allylic, so it's going to be better tertiary over here, right? So this one here is going to be the most stable. All right, so these are all allylic carbocations, right? So allylic next to a double bond, it gives us the possibility of resonance stability. All right, another type of resonance is if we have a carbocation that can be delocalized around a benzene ring. And we've already seen this before, but let's just remind ourselves here. So on the first one on the left, this is basically just a secondary carbocation, right? And because that carbocation is separated from the benzene ring by this sp3 hybridized carbon, it's not going to be stabilized by resonance. All right, there is the possibility that we could have a hydride shift like we've seen before, but let's not take that into account at this point. Let's just look at the stability of this carbocation. All right, so now the next one is secondary as well, but because this cation is at the benzylic position, or the position next to the benzene, it can be delocalized using resonance. So these electrons can come out here, and we've drawn all of these resonance forms previously. All right, it can go here, it can delocalize again. Okay, so this one here is much more stable. And at the bottom, it places these new carbocations in the range of what we've seen before. Okay, so notice that here in black in the middle is what we've learned before. So tertiary, secondary, primary carbocations. We know the order with which those go. So an allylic carbocation is about the same stability as a tertiary carbocation, so that's pretty stable. And notice that this allylic one is only going to spread the charge between primary and primary over here. So of course, if we had a carbocation that spread between primary and secondary, or secondary and tertiary, those would be even more stable than this. All right, and then it's also about the same stability as the benzylic or benzyl cation. And likewise, this is primary, so if that was secondary or tertiary, it would be even more stable. Right down at the other end, if we just remind ourselves, we have the methyl cation. That's so unstable it really doesn't usually form, and that is even better. What's even worse is this vinyl cation. Okay, we saw that when we were adding HBr to an alkyne. All right, so this is going to play, these relative stabilities are going to play into the reaction. All right, so let's just look at a few examples. All right, what about this first one? We have an alkene next to a benzene ring. Okay, so one thing to keep in mind is that we might have benzene in these reactions, but we're only going to use them for resonance. None of the reactions that we're going to learn at this point will actually react at the benzene ring itself. All right, so let's think about this first step. So this first step is going to be protonation of the alkene, just like we saw before when we're adding HBr. The tricky part here is that this is going to give us two possible carbocations. All right, I'm going to draw them here. Right, one could put the new H on this position, so we have two H's here, giving us a carbocation there. The other possibility is that we put the two H's here, the new H, so now there's two, and we get the carbocation here. All right, this is just what we had on the last slide. So which one of these is more stable? Okay, the one on the right, right? This one does not form because that's an isolated carbocation. The other one is the benzyl cation, and so now bromide can react with this, and it's going to only react at the benzylic position. So we only get this product. Okay, so this is a very regioselective reaction. Okay, it more or less follows Markovnikov's rule, even though both of these positions are actually secondary, but one is benzylic, so we're still adding the H to a position that allows the formation of the more stable carbocation. All right, let's look at the second one. We have two different alkenes, and they are separated or isolated from each other. All right, so they're essentially going to react independently of one another. So if we add only one equivalent, or a 1-to-1 ratio of this molecule, this diene and HCl, then the HCl is going to add to the side that forms the more stable carbocation, or that gets formed faster. All right, so of course that's going to go to the left side, right, because this is a more highly substituted position, so a carbocation there can form faster. All right, so we can add the chlorine here. We can get this product. All right, so it forms that position. If we add an excess, so we add a lot of HCl, we add as much as we need to react with everything in the molecule, it's going to add independently to each end. All right, so we're still going to get addition to this end, and we're going to get addition to this end, and it's going to follow Markovnikov's rule at the other end as well. All right, so let's look at these bottom two, though. This is where it really gets exciting. All right, so now we have a conjugated diene. Okay, it means the double bonds are next to each other, and so we can have resonance between those two double bonds. All right, so in this case, we are going to get two products. Okay, one of them is going to react to just one of the double bonds, and it's going to give the bromine right here. Okay, so what could possibly be the other one? We could add it to the other double bond, but the other product is going to be this one here. All right, so this with a bromine over here. So are those two the same as one another? No, not really. If we count the numbers, right? If we count where the bromine is, 1, 2, this is a 2 position. This one over here, if we count from the double bond end, 1, 2, 3, 4 position, right? So both the double bond and the bromine are in different positions. So we can look at these a little more carefully. So what's happening here, if we have an H here, we've added 2 H's here. We had an H there. Okay, so we have 2 H's here. Okay, in this case, the new H and the new bromine added across the double bond just as expected. Okay? And because they are on adjacent atoms, we call this a 1-2 addition. Okay, it's not really a numbering for naming or something like that. It's just that they're on adjacent positions. We also call this a direct addition. Okay, because they're just adding directly on there. In the other one, we've also added our H here. We have an H here, but notice that the H that we added this one, is farther away from the bromine, right? In fact, if we count the carbons, then we have 1, 2, 3, 4. So this is called a 1,4 addition. Or it's also called a conjugate addition. Okay? So we'll look at this in just in a minute. I'm going to show you one more reaction here before we get to. So we can add chlorine like this, or we could add bromine, and we're going to see a similar effect. So we're going to either get a direct addition, okay, where we have one double bond that reacts and one that doesn't. Right? Remember, and this would give us an anti-addition like this. But we could also get a conjugate addition as well. This double bond would shift over here, and we get this. All right, so we can get that one as well. All right, so let's look. We're going to look at this reaction in quite a bit more detail. For this example, we're going to start out simple with just 1,3-butadiene, and then we're going to expand into some slightly more complicated situations. All right, so let's take a look how this reaction takes place and how we get 1,2 and 1,4 addition. All right, so we start out by using one of the pi bonds as a base, right? And it reacts with HBr. We have two possibilities here for where we could put that first H, right? We could put the H on the end, and if we do that, we are going to end up with a carbocation here, right? If this has two H's, we would end up just with CH3 over here. The other possibility is we could put the the proton at this position here. And if we did that, we would get two H's here, and then an alkene with the plus on the end. All right, so this doesn't look too good, right? So for two reasons. One is that it's just a primary carbocation. We know those are very unstable. Maybe if it was allylic, we could get by, but it's not, right? It's separated from the double bond by this sp3 hybridized center. So this one is not so stable. So this is just a general thing we're going to see. If we have a diene and we're going to protonate it, there's 2 out of the 4 positions where we're likely to protonate it at. And these 2 positions are we're going to protonate on this end or this end. Not at one of the 2 center carbons. If we protonate on the ends, then we get an allylic carbocation as our intermediate. Alright, so now because we have the plus charge adjacent to the pi bond, we know that this cation is stabilized by resonance. And we can get this cation here. All right, we can get both of the types of products we've seen by just simply adding bromide to these 2 ends of this carbocation. Right, that bromide could go there. I'm going to put it down here on the bottom because I'm going to add something else in the middle. And what I would get is this product. Right, this is the 1,2 addition product. The other possibility is that our bromide adds to the other end of this allylic carbocation. And if it does that, it gives this, and this is the 1,4 addition product. Right? Remember our new H, we had a new H add here, so that's 1,2, right? Our H and our bromine came at adjacent positions. If we look at the other one, we added our new H here, so we have 1 carbon, 1, 2, 3, 4 positions apart, so that's the 1,4 addition product. Okay, so the even more interesting part of this is that we can change the ratio of these two products by varying the conditions, varying the temperature. All right, so if we do this reaction at a cold temperature, we're not going to really specify what it is, but some cold temperature, we would get this 1,2 product as our major product and the 1,4 product as our minor product. Okay, however, if we warm this up, we do it under some warm temperature, we're going to reverse the ratio of the products. So then this one is now our minor product and this is our major product. Okay? So we can change which is the major product just by changing the temperature. Okay? So that's pretty cool, huh? So if we're running the reaction at low temperatures, it means like there's barely enough energy to drive the reaction, and only the molecules, the few molecules that can make it over the activation, the lower activation barrier, go to product. So in this case, it's controlled by the height of the activation barrier. And so this is called kinetic control. All right, if we have a lot of energy, it turns out we're going to be able to allow an equilibrium, and then the more stable product forms. So this is under thermodynamic control. Okay, so let's look at kinetic first. All right, so if a reaction is under kinetic control, what it means is that it's the height of the activation barrier which is going to influence which product gets formed more, right? And the height of the activation barrier is the height from the reactant to the transition state. So let's draw out what we would think these two transition states would look like. All right, so because all we're doing in this step is reacting bromide with a cation, the transition state is just going to be a partial forming of that bond. Okay, so we could draw this out like this. We'd be in the process of forming this bond here. Right, the bromide is donating electron density, so we don't have a full plus on the carbon anymore, but we have a delta plus and we have a delta minus remaining on the bromine, right? It's given away some of its charge. Okay, so this is the transition state here. So let's look at the other transition state. Okay, in this case, we're forming the bond to that terminal position. So we have a delta plus here and a delta minus here. All right, so this is our transition state. So now what we have to be able to do is compare these two and see if we can figure out which one would be more stable. Okay, so the key thing here, or the key difference here, is where the delta plus lies. Okay, here's the delta plus here. Here's the delta plus over here. This is on a secondary position. This one is on a primary position. Okay, so what we would we'd probably propose is that this one over here is going to be more stable. All right, so we got a more stable transition state, means that there's a lower activation barrier. This one forms the major product because it's forming faster. Okay? So the other part of this is that when we have it under warm temperatures, we form the other product more. All right, so we get this product over here. At thermodynamics, that means we're just going to get the most stable product. All right, so let's compare these two. Compare the products now. Which one is more stable? All right, so they both just have no charges on them. They just have hydrogens, carbons. We got a bromine attached. It doesn't really matter if it's on a primary or secondary position. The one thing that we have different is the double bond, right? So remember, what's more stable in a double bond? Remember, a more stable bond has more alkyl groups attached, right? So this one over here would be more stable, right? Because this is a di-substituted alkene, and the other one over here only has one carbon attached to the alkene, so this is monosubstituted. So this product would be more stable. Okay, so under warm conditions, we form the more stable product. Under cold conditions, we form the product that has the lower transition state. In fact, this is showing us what we're always going to get, and I'll tell you about it a little bit more in a minute. We're going to always get, in fact, the 1,2 addition being formed faster. All right, so to try to understand this better, let's look at a reaction coordinate diagram. Okay, so here's our reaction that we were just looking at. The first step is the same in both cases, because both the 1,2 addition and the 1,4 addition both come from the same common carbocation, right? It's an allylic carbocation. Right, so we could draw that carbocation up here. Right, so we either have this, and that plus is spread out to this position. Right, so remember, this is a single carbocation, and the difference is whether the halogen goes to one end or the other of this carbocation. All right, so we saw if it goes to this end, then that gives us our most stable product, right? If it goes to this end, we're saying that that one has the lowest transition state, and so it's formed faster. All right, so there's a little bit more to this than that. Okay, so let's write out kind of some rules about this. All right, so we started out at cold temperatures, right? So what's going to happen at cold temperatures, right, if we can make it over to the intermediate, we're going to produce the product that can go over this lower energy transition state. All right, so at cold temperatures, this is what we call kinetic control. All right, so it doesn't really matter whether the product is more stable or less stable. It only depends upon which one is formed faster. Okay, the second part to this, though, is that this only works when we have low temperatures and not very much energy, because why it works is because once it makes over this low transition state, it goes down to the product, and if there's not enough energy, it can't go back up. It gets stuck down here, and it can't make it back up over here. All right, so this only really works when this reaction is now irreversible. Okay, so our rule here is that under cold temperatures we always get the 1,2 addition. All right, there's a second reason for this, though. All right, because this reason here works for our example, our simple example here, but there's going to be another reason. All right, so when we protonate on the end to form the secondary carbocation here, we've just broken the H bromide bond. So we have a bromide sitting right here, right? We just broke that bond. And there's an electrostatic attraction between the bromide and the carbocation, right? So what happens is the bromide just reacts to the end of the carbocation, which is closest to it. This is called the proximity effect. All right? So when we have cold conditions, kinetic control, we always get the 1,2 addition, not necessarily because it has the lowest transition state, but because of this proximity effect. All right, so if we warm up the conditions, then what happens is that we'll always still be forming the one with the lower transition state faster. So we get a little bit of both of these, but when it goes down to this product, there's now enough energy to make it back up to the intermediate. And so they're going to be going back and forth. It's an equilibrium, it's reversible, and eventually it all siphons down to the lowest energy point. All right? And this is the most stable product. All right, so if it's warm, then we have thermodynamic control. And in order for this to work, then this second step has to be reversible. Okay? And the main thing here is that the product we get is always the most stable one. Okay, so this one's always 1,2. This one's always the most stable. Okay, it's possible for the kinetic product and the thermodynamic product to be the same, but they can also be different. Okay? So let's look at some other examples and see if we can apply what we just learned. Okay, so what about this first one? So the first step here is that we have to figure out where we're going to protonate. All right? And because of that, we're going to figure out what carbocation is formed. Remember that the 1,2 addition and the 1,4 addition always come from the same resonance stabilized carbocation. All right, so I gave you a shortcut in determining where, or at least reducing the possibilities on where it would protonate. All right, so I said it could protonate either here, right, on one end, or here. Okay, so what we have to do is we have to consider the two possibilities, and we got to decide which one is more stable. Okay, so what I'm going to do first is I'm going to protonate here, and we're going to see what resonance contributors we get. Okay, so I'm going to add the H here. And we're going to get a carbocation right here. Right, so remember we only protonate on the end because now we have an allylic carbocation. So this one is secondary, but it's allylic. So let's draw its other resonance contributor. Okay, so I'm going to draw this one down like this. And so our other resonance contributor looks like this. Right? This is at another secondary position over here. Okay? So this is one carbocation. Okay, let's draw the second carbocation. So in this case, we're going to add the proton to this end. Let's see what we get this time. Right, so we've added a new proton here, so we have 2 there now, and we have a carbocation here. So again, by protonating at the other end of the diene, we again have an allylic carbocation, right? The cation is next to the pi bond. So let's draw our resonance contributor. Let's move this over here. plus over here. So let's compare these two. This is at a secondary position. This one's at a tertiary position. So this is the other carbocation. All right? So which one of these two carbocations is more stable? All right, so the left one goes between secondary and secondary. It's allylic. But the one at the right goes between secondary and tertiary. So that one is going to be more stable. Okay, so all of our products are going to come from that carbocation. So we're not going to form this one. Okay, so if we add bromide here, right, we're going to get bromine like this. This is our 1,2 addition product. All right? And if I add bromide to this one, bromide here, this is the 1,4 addition product. Okay? So now let's analyze these two products. Okay, we know that the 1,2 is going to be our kinetic product every time. Okay, but to determine the thermodynamic product, or the product that would be formed more at warmer temperature, we have to consider the stability of the two alkenes, right? So which one of those two alkenes is more stable? Right, so we look at the amount of substitution. So the alkene on the left, this one is tri-substituted. This one over here is only di-substituted. Right? So this one is more stable. That means that this is the thermodynamic product. Okay, so for this example, we would get the same product under both warm or cold temperatures. All right, so the key thing is, the steps here are we have to decide the carbocation. So where should we protonate to form the more stable carbocation? Notice that we couldn't really tell if we just drew the first formed resonance structure. So if we just protonated here, we get secondary. If we protonate here, we get secondary. We can't tell the difference. But we had to draw their resonance contributors. This one was secondary as well, but by drawing this one, we had a tertiary carbocation here. And so we took all of that effort to decide that this one was more stable. So we got to figure out the most stable carbocation. Then we figure out our two products. Remember, the 1,2 addition is always a kinetic, and then we have to look at the two products to determine which one has the more highly substituted double bond. That's going to be the thermodynamic one. All right, well, we better do one more. We're going to have to add in a slide for this one, though. Okay, so let's write this one out. So we are starting with this diene right here, like this. All right, and we have to decide where it's going to protonate. Okay, so we are going to add HBr, right, plus HBr. Remember, we have two possible positions to protonate. This one or this one. Okay, so let's try. Okay, I'm going to protonate first here and then here. Okay, so let's see. Okay, if we add a new H here and here, then we get a carbocation there, like this. All right, let's draw its other resonance form. Push the electrons this way. and we get this carbocation. Here was the H's. Alright, so that's one possibility. Alright, so let's draw it on the other side. Now we're going to add the H to that number 2 position. Here's our H. Alright, so that puts a plus here, double bond here, and a methyl group there. Alright, resonance. Get a plus over here, double bond here, H, methyl group. Okay, like we did before, here's one carbocation, here's the other. Which one is more stable? Alright, so let's look at where the carbocation lies. Alright, so this one is tertiary, and this one is tertiary as well. That looks pretty dang good. This one is secondary, and this one is secondary. Alright, so we're not going to form this one, and the one on the left is more stable. Right? So let's figure out our products. So from this one, if we add bromide to that, the bromide goes where the cation is. We end up with our bromide here, double bond here, like that. We do this one, get this product. Are they different? Dang, these two are the same. Same, so again we only have one possible product. So in this case it doesn't really matter whether we use warm or cold temperatures. Alright, so remember these steps that you have to go through. You have to look at the diene, you have to figure out where to protonate it. We're only going to consider 2 positions to protonate. One on this end and one on this end, not the 2 in the middle of the diene, right? Because that leads us, if we protonate on the ends, it leads us to a allylic carbocation. We have to try both, taking into account resonance, right? And then we can calculate, we can figure out the 1,2 additions, 1,2, 1,4. Turns out in this case the 1,2 and the 1,4 are just the same products. Alright, so I hope you're following me on this. We have now looked at 2 types of reactivities that can vary due to resonance, right? We looked at acid-base chemistry, and we looked at these additions to dienes, and we saw that we could have either kinetic control or thermodynamic control. Alright, so in the last video for this chapter, we're going to see a new reaction, and this one is going to really blow your mind. It's called the Diels-Alder reaction.